The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.
Okay, so we'll get started. As always, review. Does anyone tell me what Bayes' rule is? Intuitively or mathematically? Okay. So Bayes' rule is kind of like the reverse, right, of what we're given. So if you want the probability of some event given B, then you'll have to do the probability of A times the probability of B given A over probability of AI given probability of B given AI, all the way to probability of AN given probability of B. So that probably a little hard to remember the formula, but if you think visually, it's like if you have a sample space, right? And say you have some random event B, but you don't actually know what this is. All you know is that you have like A1 maybe, and you know the probability of A1 and B. And then you might have like A2, A3, etc. until AN. Right, so n could be like the number of partitions. So Bayes' rule is figuring out probability of A given B when you're given these chunks. Does that make sense? Guys, need more time? No? Okay. So what's the total probability theorem? Basically just wrote it so you can point it out if you want. Yeah.
Isn't it the thing on the bottom?
Yep. So this is the total probability theorem, which gives us PB, right? So it's called like total because you have to have every one of these A's that have B in it. So if you like know A1, A2, and A3, but you don't know this part, that's not complete. Not total, so it won't work. So you have to make sure you have all of that. This is too high. Okay, does that make sense? Okay. And if I told you that A is independent from B, what does that mean intuitively?
P of A given B equals P of A. Like, it doesn't, they're not related at all, so you know one, it doesn't help you change anything here. The other is.
Mm-hmm. So B basically doesn't give you any information about A. No new information about A. Yep. And that can be reversed. So if A is independent from B, B is also independent from A. I won't write that because I figure that makes sense. Okay, so how do we test for independence? What's that equation? I think you just said it, but anyone else? Yeah?
P, put the total probability theorem on top. Then you put P parentheses A parentheses.
Oh, wait. Can you say that again?
You put the total probability theorem on the top of the fraction.
You mean like this?
Yeah.
What would I put here?
A, B.
A something B?
A plus B.
Union. Yeah. Yep.
Over. P parentheses A parentheses.
This?
Yeah. Yeah.
Anyone have another answer?
Isn't it the probability of A is equal to the probability of A intersect B over the probability of B?
Yeah. Okay, so like for you got part of it if you switch these, but because this itself is just an expression, you're not saying like equal to what. So you can't really evaluate it while given some kind of result, right? So if you're just giving like y, that doesn't really tell you if that's a test or not. But like this does, because this has to hold true. Okay, so this is right. Does everyone see why that is? So we usually actually write it with PB over here because we don't like dividing by 0. So if we just move it over here, that takes care of it. So you'll get PA, PB. Okay, so we like to write it like that, but they are essentially the same thing. Yeah, just because of the divide 0 thing. So like here you can put in 0. Sorry. Okay. Does that make sense? Okay. All right, so we actually didn't get to conditional independence last class, so we're going to go over that now. Okay. Where's that eraser? Do you guys need this? Okay. So we have this for independence, right? And if we want to do conditional independence, we just do given C, right? Because that's what conditional means, given something, right? And you can also see it the second way, which means that even if you're given B and C, the addition of B doesn't mean anything. So how do we get from the first to the bottom? So you have is this okay to read? It was kind of messy. Okay, so another way of writing this is if we have like A union B union C over PC, right? That's kind of like we did with conditional probability, right? And then you're given in that equation that this is PA given C, PB given C equals. And the way to get from here is using the multiplication rule. So you have like probability of C, probability of B given C, probability of A given B and C. Does this make sense? Over probability of C. So if you don't fully understand that, you can think of it as like C, a tree, right? And then B, not B, and then A, right? So that top part is just like probability of C, probability of B given C happened, probability of A given B and C happened. Okay, does everyone see that? Okay, so then these two cancel, these two cancel, and then you're left with this part. Okay, which is essentially that second line. So you can use either of those depending on what you're given in the problem. Does that make sense, how we got from one to the other? Okay. I'll give you more time to write it. Okay. Okay, so we have an example. Wow. Okay, so we have two coins that are blue and red, but they're biased. So the blue coin has heads 99% of the time, and then the red coin lands head only 1% of the time. So what we're doing is first we're choosing one of these coins at random, and then we're flipping it twice. Okay, does everyone understand that problem space? Okay, so the way we broke it down is that event 1 is H1 means the first toss is a head, and the second event is H2, which means the second toss is a head. So the question pretty much is, are they independent of each other, these tosses? The thing is that they're independent of each other conditionally. So if you already know what coin you're given, then each toss is independent. So I'm going to prove that. Okay, so we're going to assume B, which means we got the blue coin. Okay. So are they conditionally independent? You have that equation again. You have P H1 union PH2 given B. Is that equal to probability of heads? First toss is a head given B plus probability of second toss heads given B. Okay? So that's what we're trying to answer right now. Does everyone understand how this is conditional? Like you're given that you have B? Okay. So this is kind of obvious. If you're given B, then it has 99 times 99 chance, right? Being heads. And then this is 0.99 times 0.99. So obviously they're equal. So they are conditionally independent. But the next question is, if you don't know which coin you have, if the tosses are still independent. So that's answering the question, okay? So this was our original test for independence, right? There's nothing given, so we don't know what coin we have. So now we're trying to answer, are these tosses independent without given information? You can see the difference? Okay. So how do we calculate this? Probability of the first toss being a head. Okay, so we're going to do this like using the total probability theorem, right? So we have probability of first head given that it's blue, plus the probability that we got a blue coin, plus probability that we have a head given that it's not blue,